Okay, your first set of notes in Chapter 3 is going to be on the definition of the derivative of a function, right, the definition of a derivative, and that is from sections 3.1 and 3.4. So the basics of it are in 3.1, and then the applications are in 3.4. So I thought it made more sense to combine those. And then the second part of 3.1 is going to be in your next video, and that's on differentiability of a function, and that'll be your 3.1 and 3.2 video. So it kind of makes sense if you look at it from my point of view, why I'm kind of mixing things up for you. Okay, so recall that you know what the definition of a derivative of a function is. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And the derivative of a function at a point x equals a is f prime of a equals the limit as x goes to a of f of x minus f of a all divided by x minus a. Or I could replace every x value in here with an a, and I get the same thing. Okay? These all should look very, very similar to your slope function because it really is giving you the slope, only instead of a slope at 2 different points, it's just a slope at 1 point. Okay, so our first example says find the derivative, and I'm going to use the definition of a derivative. So I am going to use this formula right here. Actually, I stole this from the book, and they wanted me to use that. I just did not write it in the question. So I have the limit as x goes to, my a value is 3, right? I don't have to find it in general because it's only asking me at 3. So the limit as x goes to 3 of f of x, so that's just my original function, x plus square root of x plus 1, minus f of a. Well, if I plug a, which is 3, into this function, I get square root of 4, which is 2, all divided by x minus 3. So now I need to evaluate my limit. So I try plugging in x equals 3, and I get square root of 4, which is 2 minus 2, which is 0. All divided by 3 minus 3, which is 0, 0 over 0. Does not work. I have to do something differently. And what I do differently is because I have the square roots, okay, I multiply by the conjugate. So, in other words, I'm going to rationalize the numerator. So I'm going to multiply by square root of x plus 1 plus 2, the same thing as the top, only opposite sign. And why am I doing this? Well, because it allows me to cancel things so that I no longer get 0 over 0. Just like I would if it was a polynomial over a polynomial. Okay, so now in the numerator, I have, right, I'm going to FOIL, so the first one times the first one just gives me x plus 1. And then my outer, I have positive 2 square root of x plus 1. And then my inner gives me negative 2 square root of x plus 1. And those cancel out. So now I just have my last, which is minus 4. In other words, it's the difference of squares. And that's what you're doing when you multiply by the conjugate, is you're making it the difference of squares so that you no longer have your square root. Right? If you had outer and inner, then you would still have your square root. In the denominator, right, do I want to multiply this whole thing out? Well, no, because the whole point behind this was that we could cancel something. And if you take a look at this, this is going to give you x minus 3, and it will cancel with this x minus 3. So let me just rewrite it as it is. X minus 3 times square root of x plus 1 plus 2. And, like I said, this is going to be x minus 3. So therefore, it will, oh, that's interesting. It will cancel with the denominator, and I'm just left with 1 in the numerator. So now I have limit as x goes to 3 of 1 over square root of x plus 1 plus 2. Okay, now that I've canceled something, I should be able to plug in x equals 3, and hopefully it'll all work out. So now, if I take this x, and it goes to 3, then I get 1 over square root of 4 plus 2, which is 1 over 2 plus 2, which is 1/4. And I evaluated the limit, so I no longer have to write limit, right? Meaning, evaluate meaning that I plugged in x equals 3. And there's my answer. I can check this because I taught you guys how to do the chain rule in class, right? This is the same thing as x plus 1 to the 1/2. So the derivative of this would be 1/2 times, keep the inside the same, x plus 1 to the, decrease it by 1, negative 1/2, times the derivative of the inside. Well, the derivative of x plus 1 is just 1. And now I just plug in x equals 3. So this gives me 3 plus 1, so 4 to the negative 1/2, which is 1 over square root of 4, which is 1/2, times 1/2 is 1/4. So we did do it correctly. Next, we have f prime of x gives us the instantaneous rate of change, or in other words, just our rate of change, right? It doesn't say whether it's average rate of change or instantaneous rate of change. It's asking you instantaneous rate of change of your original function. If s of t is a position function at any time t, then the derivative, which can be written as s prime of t or ds dt, right? They're saying derivative of s function with respect to t equals your velocity. The velocity at any time t. Okay? That makes sense because you're looking at how your original function's changing, right? If you're looking at how your position is changing over time, well, that is your velocity. Okay? Velocity can be positive or negative. However, speed is always positive. So speed, I just took the absolute value of all three of these expressions right here, and it is always, always positive, right? Velocity is speed with direction. And the last thing is acceleration, which is our second derivative. Okay, so we write a second derivative like either one of these. Okay, so the second derivative of our position function, which is the second derivative of s with respect to t, and you always put the little 2 here and then the little 2 here. It's just how it works. Which is also equal to the first derivative of our velocity function, right? So if I have my position, I have my velocity, and I have my acceleration, then I take one derivative, and I take a second derivative, right? So here to here would be two derivatives, right? The second derivative of my position function is acceleration, and the first derivative of my velocity function is also my acceleration. Okay, so let's do an example. A particle moves along a line so that its position at any time t is greater than or equal to 0 is given by this function, where s is measured in meters and t is measured in seconds. First question says, find the instantaneous velocity at any time t. So all we're doing is taking the derivative, and that's very, very easy because I have a polynomial. So I just multiply my coefficient by the exponent and decrease the exponent by 1 for all of these terms. Next one is our acceleration. So we are just going to take the derivative of the velocity function we just found, so negative 6t plus 14. C, when is the particle at rest? The particle is at rest whenever your velocity is 0. Okay, so now I have a quadratic equation. And in order to find when a quadratic equation is equal to 0, we either need to be able to factor it or do the quadratic formula. And this is definitely a calculator question. So, well, I mean, you could find the exact one, but because it's a word problem, they wouldn't expect you to give the answer as just a radical, right? They would want you to round it as a decimal. So, I'm just going to do this on my calculator, put this into y equals, and then calculate the 0, and I get t is approximately 1.451, or, let me find the other one. And I'm always going to do 3 decimal places because that is what you have to do on the AP exam. So here are the 2 different times where it is at rest. Okay. So at 1.5-ish seconds and a little bit over 3 seconds, it is at rest, both those times. Okay, so describe the motion of the particle. At what values of t does the particle change direction? Well, it changes direction whenever my velocity function changes direction, right? So let's take a look at our velocity function. Well, I know it's 0 at 1.45, 1, and then I also know that it's 0 at 3.215. Well, now it's a parabola, so therefore it's either looking like this or like this. Well, how do we know if it opens up or down? My leading coefficient is negative, so it's going to look like this. Okay. I don't care the height of it, right? I don't care where the vertex is. All I care about is where it's positive and negative. And if I already know the zeros and whether it opens up or down, I know that it looks like this. So, obviously it doesn't make sense when t is less than 0, or I guess it does make sense. It does work when it equals 0, but it doesn't work when it's less than 0. So I'm going to say for t is between 0 and something. Well, between 0 up to 1.451, then my velocity is negative. Having a negative velocity means that my particle is going in the negative direction, which means it is going to the left. Okay. And then at 1.451, it is going to stop, right, because my velocity is 0. And then, where am I here? And then between those two, it has a positive velocity, so it's to the right. It's going to the right, and then it's going to stop, and then it is going to the left. Okay? So let's write all of that out. Okay, so when t is between 0 and 1.451 seconds, then the particle is moving to the left because the velocity is negative. At t equals 1.451, then it is at rest. And then between 1.451, oh, and what? Does it ever tell us when it stops? No, it does not. Wait. So here to, oops, I missed it. Here to, I'm skipping ahead. I have to go to my next 0. Okay, from between here and here is in the positive. Velocity means that it's moving in the positive direction, so therefore it is moving to the right. Of course, sometimes this would be up and down, but it just happens to be that this is moving along a line, so it's going left or right. And that t equals 3.215. It is at rest again. And finally, as I was trying to skip ahead to before, right, it doesn't tell me when it stops moving, so I can just say t is greater than 3.215. It is moving in a negative direction, so therefore it is going left again. Okay, so a lot of times you're going to say, the question will say if it starts off at the origin, and then we don't know how far it's going, right? But it's going to start off going to the left for a little while, and then it's at rest at 1.451, and then it goes to the right for a while. I don't know how far. And then it goes, and then it rests again at 3.215, and then it goes to the left again. And it does that forever. And it keeps on going to the left. Okay? So it does something like that. And these endpoints right here are when your velocity is 0, right? In other words, you're changing your direction. So you can't go from a negative to a positive or a positive to a negative velocity without having a velocity of 0. Okay, and our last application is marginal cost and marginal revenue. And this is just the rate of change of your cost. So it's a derivative of your cost function. And the rate of change of your revenue function. So it's just your R prime of x, right? Your derivative of your revenue function. And this is defined as the extra cost of producing one more item. So if we're producing 100 items, then the C prime of 100 will give you the extra cost, right, the cost to produce 101 items. Okay, because that's how much it changes if you increase your X value by 1. And the same thing for revenue. It's the extra revenue that you're going to earn if you sell one more item. Last example, suppose that it costs this much, here's our cost function, dollars to produce X hats when 5 to 10 hats are produced, and that here's my revenue function, and that gives the dollar amount, the dollar revenue from selling X hats. Your shop currently produces 10 hats per day. Find the marginal cost and marginal revenue. Sorry, my throat's really bothering me. So, marginal cost. I want to find C prime of 10. So first I will find C prime of X. And again, I'm just taking the derivative of a polynomial, so that is 3x squared minus 10x plus 12. And I want to know what the marginal cost is when I am producing 10 hats. So I just plug 10 into that function. So 3 times 10 squared minus 10 times 10. My mouse does not want to work very well today. Plus 12. So I get 3 times 10 squared, which is 300, minus 100, so 200 plus 12 is 212. And since this is marginal cost, okay, then it is dollars. So it's going to cost $212 to produce each additional hat, as long as we are around that time. Okay, so if we're already producing 10, then it's how much more it's going to cost us to produce the 11th one. Right? Maybe once we get up into higher numbers, then it wouldn't cost us quite as much in order to make an additional hat. These are some very expensive hats. And now for our marginal revenue, we're going to do the exact same thing. I don't know why I can't write with this. 3x squared minus 4x plus 8. Just the derivative of a polynomial. And now plug in 10. And this, oops, I'm taking the derivative again. I got a little anxious there. Oh, oh. So I just plug in 10 into my function. So I get 3 times 10 squared minus 4 times 10 plus 8. So I get 300 minus 40, which is 260 plus 8, so 268. Right? So this is a good thing, right? When I am producing 10 hats, then it is going to, and then by selling that 11th hat, then I am going to make $268 extra. So therefore, if my marginal cost is greater than my marginal revenue, then I should totally make that additional hat so that I can make the difference of those two in my revenue, right, in profit. Which is revenue minus cost. Okay, so that is it for me. You have 4 questions to do from homework. One is just a basic question when we're talking about the definition of a derivative, just like the question in your notes. And then you have 3 different application questions. Again, they should be very, very similar to what I just did. So that is it for me, and I will see you guys in class.